Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This is part of the first series on impulse and momentum, and it focuses on specifically impulse. We've already had the work energy principle, which is expressed as the work done is the change in kinetic energy. The work done is defined by the product F times D in the case that the force is constant, and the change in kinetic energy is of course the final kinetic energy minus the initial kinetic energy. Now we want to look at a different principle this time, and for this purpose we want to start again looking at the left as a force diagram. A constant force acts on a mass m producing an acceleration a. The right hand diagram stores the information that initially above the body, the particle, is the initial speed, which is a direction to the right, so it's a velocity with magnitude u, and afterwards there's a velocity of magnitude v also acting on the same line to the right. Now we can analyse this using Newton's second law, which tells us that F is equal to ma. We can also use suvat, because if the force is a constant, so is the acceleration, so it's appropriate to use the equation v equals u plus at, and v and u have there exactly the meaning they have on the diagram up and to the right. Now from the first equation we can deduce that the acceleration is the force divided by the mass, and that can be substituted into the second equation to say that v is u plus f over m times t. Now we don't like fractions, so we multiply by m and we get mv is equal to mu plus ft. Now this is starting to look as if it might have something familiar about it. mv is momentum at the end and mu is the momentum at the beginning. So let's express it more helpfully as ft equals, and it will be mv minus mu. Now there, in very simple terms, we have the impulse momentum principle, which says that the change in momentum, the final momentum minus the initial momentum, is equal to what we call the impulse. And we can see from this that impulse is defined for a constant force as the force times the time it acts. Now that makes an interesting contrast or comparison with the principle of energy, as we shall see in a moment. But meantime, let's focus on what we've got here, which is that the impulse is defined as force times time, and that the impulse momentum principle is expressed as the impulse equals the final momentum minus the initial momentum. And a neater version of the derivation is there on the left. So, to make the comparison I just mentioned, above we've got the work energy principle, which is essentially a relationship between scalars. Work, you'll remember, is a scalar, as also is energy. On the other hand, below we've got the impulse momentum principle, which looks in some ways very similar, but here it's a relationship between vectors. Impulse and momentum are alike vectors. And the final thing to note is that for both impulse and momentum, the units are Newton seconds. Well, let's look at these ideas in a simple context. There's a situation described in exactly the way we exemplified before. The initial speed is above and the final speed is below, and we want to find the force used. Now, instead of doing it using force acceleration, we're going to do it by the impulse momentum principle. So we show on the diagram not the force but the impulse, which is the 4 times the f for the unknown force. So our impulse momentum equation can now be invoked to say that 4f is the final momentum, the 2 times 12, minus the initial momentum, which is 2 times 5. So following that through, on the right we have 24 minus 10, 14, divided by 4 is 3.5. So finally the force is 3.5 newtons. Now notice the footnote here to stress what we did, which is that the diagram needs the impulse to be shown, and it's better to use impulse rather than force if we're talking about momentum, but it needs to be one or the other. Now let's look at another problem which is just as simple but with slightly more complicated numbers. If we put what it says, there's an auspicious 4 come in there, let's get rid of that. If we put the information in the question on the diagram, we've got the 3 kilograms showing, and we've got a change from 5 millimeters per second to the right. We'll take it to 4 meters per second to the left. So if we apply the impulse momentum principle, we can see that we're going to get an impulse on our diagram, and sensibly it will be shown to the left because the end result is a momentum to the left. If we showed it to the right, it wouldn't matter. If we apply the impulse momentum principle consistently with the signs, we then end up with our answer for I as negative. So if we apply impulse momentum where positive is to the right, look out, that means that the impulse is minus I because it's to the left. Similarly, the final momentum is 3 times minus 4 because that's to the left, whereas the initial momentum is certainly to the right and it's 3 times 5. So the calculation tells us that minus I is minus 27, so I is 27. So the impulse is 27 newton seconds, and it's a vector quantity, so we must make clear what the direction is somehow using the information in the question. So I've said it's in a direction opposed to the original velocity. I could have said it's in the direction of the new velocity. A large impulse, well, 27 is big compared with the figures given in the question, effectively is turning a momentum to the right into a momentum to the left. It stops and then pushes back the particle in question. Okay then, so there we have the statement of the impulse momentum principle. On the left we've got a diagram with forces and accelerations. On the right we've got one of these information stores about what happens during a motion. Now let's look at collisions. Consider 2 billiard balls in collision. What happens? From the point of view of what you see, in an instant both change direction of motion and there's a loud sound generated at the moment of impact. That should tell us that some energy is given off. So this is definitely a context where we don't think in terms of conservation of energy. The same is true for a ball bouncing off a wall or a cricket ball rebounding from a cricket bat. In each case there's a quite sharp sound, and something happens so quickly that you'd be hard put to see it actually happening. You see what happens before and what happens afterwards. Now, how can we model this in mechanics? Well, there's a careful discussion, theoretical discussion could be held about this, but this is just a summary. We model a collision by saying it's an event which takes place over 0 time. 0 time, yes, actually a very small time, so that there's an impulse between the two bodies, and that's what determines what happens. The impulse of all other forces taken to be 0. So in an impact, we say that in a collision or impact, we consider only the interaction forces between the bodies, and we say that they have a significant impulse, even though we pretend, if you like, that the time is 0. So let's now consider an impact of a ball with a wall. We've got an incoming speed of 5 and an outgoing speed of 3. And because of what we just said, we don't need to consider gravity or anything else, because the impact will all be in 0 time when nothing else can have an impulse. So the model we adopt for the dramatic change is that speed in direction is achieved solely by the impulse generated by the interaction with the wall. We ignore all other forces which may be acting on the ball, like gravity or air resistance, before or after the collision. So there we have a diagrammatic representation. The calculations go from the impulse momentum principle. We say that if we're trying to find the impulse from the wall, since we know its momentum before and after, the impulse must be the change in momentum. So we can see there that doing the calculations, note again the direction to the right, so the I shown on the diagram comes as minus I in the equation, and the final momentum is 2 times minus 3 because it's to the left, not the right, and that's from that is subtracted the 2 times 5. So we end up with I equals 16, and the impulse which the wall imparts to the ball during the almost, we say in modelling terms, 0 time is 16 Newton seconds. So there's the answer in context with the units. Notice the importance of saying the direction, even though in this case it's pretty obvious. And notice again that a large impulse stops the ball in its tracks and sends it back on the way from which it came. Well, that ends this video presentation. The next one in the same series looks at the principle of conservation of momentum, which has obvious echoes but is actually quite different from the principle of conservation of energy. I hope to be with you later to explore that.